Welcome back, everybody. We're going to continue our explorations of Fall 21 Test 3 mechanisms. This one, we're making a allylic ether, phenyl allyl ether. And why would I do such a thing? A phenyl allyl ether is good for doing a Claisen rearrangement. And let's start. This is pretty straightforward. We're going to do this one in part D in the same video because this one's kind of short. Scribble off the H, scribble off the potassium, put a lone pair and a minus. Get our red first, blue second going. Blue second. And here goes acid base to generate an anion. Anion with a lone pair. Good thing we already have a lone pair, because in the next step, that lone pair attacks the carbon with a leaving group. Backside attack, and you are finished with that first step. That is the result. Second step, the heat. Remember, it's one of those reactions involving 3 arrows only. And it's always the same. If you count from the allyl portion, 1, 2, 3, 4, 5, 6, it's always the same. You're going to get a carbonyl between 4 and 5. My 5 needs to move. All right. Oh, all of those are the same. I got it. First thing, carbonyl forms. And that generates a nucleophile that attacks 1, resonates into 2 and 3, completing what looks like benzene resonance with 3 arrows. Yeah, it's a pericyclic reaction. It doesn't give this, it gives the tautomer. What? It gives the isomer related through tautomerization. And that's there. And I'm not making it look pretty, but I'm just drawing what I see. And we got a new bond here to our aromatic ring, 6, 5. And we got a carbonyl. And we have an H right here. That can't be there at the end because there's no H on the same position there. It's time for tautomerization. Pi is going to grab an H. Can't reach it. Ring size would be 4 in the transition state, counting atoms. 1, 2, 3, 4. Whenever the transition state involves ring size 4 or less, you can't do it within 1 molecule. You must indicate you know that. You must indicate it happens between 2 molecules. You must use intermol on the arrow that says molecule A grabs it from molecule B. And don't forget to make your ring aromatic again. The strong driving force for this reaction is re-aromatization. And that's the end of that. The best part is you got a sigma bond between 2 carbons without much effort. Up to here, those are 2 facile reactions. That means easy. And moving on to part D. Yes. You're saying, why does he keep putting these review reactions on here? Well, the reason we learned this review reaction was for this time, because you learned in chapter 23, you can't put a primary carbon group on benzene directly. You first put a ketone on, like we did in part A, and then you can reduce the ketone using a Wolff-Kishner or a Clemenson. This is a Wolff-Kishner. It is very important that you review the Wolff-Kishner mechanism because you will probably be doing it again next Wednesday. And here it is. And wonder if we can save any steps? Probably. Let's go Control Z here. Let's put the lone pair underneath. Not in red though. Let's put red first. Wow. There's some dead spots up there. Blue second. We're going to attack carbonyl, generate an O minus. You know, it looks like that lone pair might be on the O. Me no like that. I don't like that at all. I do not want that confusion. X, Z, Z, V. Okay. The lone pair back on top. It's giving me fun hard time. There we go. Had my hand on the screen over there. I'm also going to draw one of those H's sticking off right there. And I'm going to scribble out the 2. If I'm lucky. There, good. Nitrogen is attracted to the positive carbonyl. Pi breaks, becomes lone pair. That's an O minus. O minus sees that H on the ammonium ion. What ammonium ion? Well, you just made a 4th bond to this nitrogen. Yes, it's now an ammonium ion. Step 2, ammonium ion gets deprotonated by the O minus you generated with the red arrows. Can't reach. Another ring size 4. There you go. I obliterated my NaOH. That's okay. We'll redraw NaOH when we need it. Okay. What's going on now? We need to draw this whole thing. Wolff-Kishner. And I'm getting used to drawing this thing now. Yep. We have an O with an H on it. We're about to make an imine, by the way. Special imine. This thing still has one H. There's an NH2. Nitrogen got its lone pair back. It's going to push off hydroxide. Don't be alarmed. Normally I'm saying at this time, hydroxide, a lousy leaving group. Don't do it. If you have a reaction where there's already hydroxide present, making it leave from another molecule is definitely okay. You cannot kick off hydroxide if there's HCl or H2SO4 or any strong acid present. We do not have that scenario. And now you've got N double bond C. It's an iminium. Iminium. Better put the yum. There's the yum. It is time to neutralize your iminium. Okay. Hydroxide be a good choice, huh? Just kicked it off. Where do you want to put it? Down here? And it's coming to get the H. And you've made an imine, special imine. Boom here. Okay, not that much. All right. And we've got an N double bond C. NH2. My goodness, this is really good to do this one right after doing this one. Right here. Because you're at a juncture that looks a lot like what we're about to do right here. We did a tautomerization, and then we did a elimination. And those looked very similar to each other, and these will as well. That was from our previous video. You're going to need hydroxide and water as your acid-base conjugate pair. Can't use HCl when there's no HCl. Why am I putting water near the pi and HO minus near the H? Well, because the HO minus needs to take an H. Sigma becomes pi. Straight up tautomerization, everybody. We're eventually going to get to that product. In the meantime, I'm getting pretty good at drawing this thing. I may have just jinxed myself. And what do we have down there? We have a new H that I don't need to show. We have an N with a double bond to N with a single bond to H. It's about time to make that into this. Doing about the same thing we did in the last step. Put your HO minus near your hydrogen. Put your HOH near the sigma bond that needs to become a sigma bond to H. Grab the H, sigma becomes pi. This sigma picks up a proton and generates your catalyst again and picks up a second proton right there. You get two new H's right here. You want to see them in green? No, you don't need to see them in green. There's CH2 where you used to have a carbonyl. All right, what's going on here? We need no mechanism. What's going on here? What's going on? There's a lot going on, but only one point for it. I see oxidation of a phenol to an orthoquinone. Take a look at video from yesterday, where we did the mechanism for this reaction. Yeah, you'll see that if you have chromic acid present, you get an orthoquinone if the para position is occupied. We did that. So now just reflect on, the same exam. Sometimes there's clues available to us. We're gonna go back here. Yeah, if you have a phenol and you react it with chromic acid, water, and sulfuric acid, you get the orthoquinone on the page we're looking at. And then we'll just worry about the other piece when we get there. Where am I? You want to use CrO3 H2SO4 AQ is one of your methods of generating chromic acid. So that takes care of making the quinone. What takes care of taking a benzylic carbon with at least one H on it? Here it has two, but with at least one H on it, becoming a carboxylic acid. Oh, I don't know. That's chromic acid oxidation as well. Yeah, although I disagree with my product a little bit. Yeah, I do. Never caught this the semester I put the exam out there. Yeah, this wouldn't be the product, but to get the other carboxylic acid, you're going to need the heat. And this isn't the real product here. My apologies. We're going to pretend it was the real product. But I want you to learn that reaction because we learned it at the end of chapter 21. The benzylic carbon becomes a carboxylic acid. And this carbon I didn't even teach you. This is the other carbon. It also becomes a carboxylic. So it's not even the product. I feel embarrassed. Yeah. Yeah, that's still an extra carbon, isn't it? We don't gain
Dr.
any carbon. Yes.
What's the mechanism called?
Oxidation. We didn't do the mechanism for oxidation at the benzoic position. It was talked about at the very end of chapter 21, Introduction to Aromatic Compounds. So we're going to look at that. You treat the benzoic carbon, not this one. This one doesn't have any H's on it. It has to have at least one H. And as soon as you hit that with chromic acid and heat, you get a carboxylic acid there. Generally, I don't ask about the other carbons that used to be attached. And I didn't expect you to know this would be a CO2H here as well. But I do expect you to know that the benzoic carbon should be a CO2H. And I don't know how we're going to redo the mechanism. We'll think of something. Yeah, when I come back, I'll just adjust this so it does something more real. And we'll come back for part E. See you then.